Hello, good evening, and welcome to the problem solving session. So, today we have our session 10 of the course Microwave Engineering. The topic of discussion for this week 10 was about ferrite devices, wherein the different topics covered in this particular week 10 is starting with microwave propagation in ferrites, then Faraday rotation, then isolators. So, and also circulators. So, you are well aware of the theoretical concepts, I believe. So, as you know, what are ferrites, or we call it as ferrimagnetic material. So basically, the ferrites or ferrimagnetic materials, they have electrically uncharged materials that attract. So in general, about ferrites, I had something to talk about the epsilon r and mu r. So I believe you all know what is epsilon r and mu r. So that is the relative permittivity and relative permeability. So generally for a non-magnetic material, mu r will be unity, but here it's a ferrimagnetic or ferrites. In case of ferrites, this value of mu r will be very high, and the value of epsilon r, that is the relative permittivity, is greater than 10. Okay, so that is some information I wanted to talk about ferrite devices or ferrimagnetic materials in general. Okay, then I hope you know the basic of isolators and circulators and the principle of Faraday rotation. So as we come across some of the questions, we'll discuss them as and when it comes. Okay? Can you mute yourself? There is some noise, I think. Okay, thank you. Okay, fine. Okay, so let's start with a few questions. So as and when it comes, we'll discuss the theoretical part also. So let's start with this. If omega naught is the Larmor frequency, so this is, please take it like this, omega naught is the Larmor frequency, and omega is the frequency of AC magnetic field. Okay, so omega is the frequency of AC magnetic field. For omega less than omega naught, mu less than k. So in this case, we need to have an idea of what is mu and k. So let me represent mu as mu naught into 1 plus omega naught omega m divided by omega naught square minus omega square. So it's very clear, omega naught is the Larmor frequency and omega is the frequency of the AC magnetic field. Okay. Now, let me complete the expression for K also. K is mu naught into omega m divided by omega naught square minus omega square. Okay. So now here, if I take omega less than omega naught, okay, for a frequency, whenever the frequency of AC magnetic field is less than the Larmor frequency, so omega and omega naught. So if you look at the two terms, the numerator term, considering the numerator term, so you can notice that if omega is less than omega naught, obviously k will be less than mu. Okay, so mu less than k is a false statement. Yes, I think there is a response in the chat. Yes, Arun Raj, that is true. Sorry, that's your answer is right. It's a false statement. Okay, I hope this is clear. Now moving on to the next question. For omega less than omega naught, the angle phi by which the direction of polarization rotates as a plane wave propagates along the z-axis in a magnetized ferrite becomes more negative with increase in z. So for this, we need to know what is this phi. That is, what is that phi? So the question is about this angle phi. What is the phi? That is the angle by which the polarization rotates, or we can call it as polarization rotation angle. Okay. So that is as the wave is propagating along z axis. So you assume that the wave propagation is along z. So what is phi? Let me write this phi. So the polarization rotation angle is, maybe we can write it like tan inverse of Ey by Ex, or we can also write in terms of propagation constant and the propagation distance. Okay. So to write in terms of propagation constants, we can write it as beta plus minus beta minus divided by 2 into z. So if you notice this equation, in this equation we have a term z, that is the distance along the z axis, or if you ask, if you say like depending on the distance covered, the phase will change. So this, as this z increases, so the statement here is with increase in z, this phase by which the direction will have a rotation, that will become more negative. So that is correct. So if you look at this, if the z increases, the total magnitude increases because it is negative, it's totally more negative. So this is a true statement. So we will come across these terms beta plus and beta minus in the coming questions. So please try to understand beta is the propagation constant. So we'll discuss them detail in the upcoming question. So, okay, I think we can move on. Yes, I have a chat response also. Yes, that's a true statement. Okay, now we have a question here. If in a ferrite medium, beta minus by beta plus, okay, so this is beta minus divided by beta plus. So it's a ratio. If that ratio is 0.5, then what is the value of mu by k? What is the value of mu by k? So how do we find it? First of all, we need to understand what is beta minus and what is beta plus. Okay, we know in general beta is what? Omega root of mu epsilon. But in case of ferrimagnetic materials, what we need to do is beta minus, say, let me just write in general, beta plus minus is omega root of epsilon into mu plus minus k. So if you notice, whenever it's a ferrite device or ferrimagnetic device, the component mu plus minus k is coming into picture. So beta plus minus, so if it is beta plus, it will be mu plus k. If it is beta minus, it will be mu minus k. So that is the understanding of beta plus and beta minus. So if I take the ratio like beta minus by beta plus, what will happen? The omega square root mu epsilon will cancel. So what remains is mu root of mu minus k divided by root of mu plus k. Okay. So if this is 0.5, if this is 0.5, taking the, say, the easiest way to solve this is taking square on both sides. So mu minus k by mu plus k is equal to 0.25, taking square on both sides. Then, can we now find out the ratio mu by k? It's just a simplification. I request everyone to try it. And please post your responses in the chat. I hope everyone is trying. Yes, right answer. It is, as you both have mentioned, the right answer is 1.67. So once you just simplify it, you will get the ratio. Yes, thank you. Thank you for responding. So the right option is 1.67. Okay. Now let's move to the next question. Okay, this is again a true or false question. Just see this. Microwave circulators are designed using the property of Faraday rotation in the ferrite material. Is it true or false? Very simple question. Yes, I need responses from everyone. Are these microwave oscillators based on the property of Faraday rotation in a ferrite material? True. That's true statement. And I would, at this point, I would just like to, um, okay, I would like to just talk about the working principle of Faraday rotation isolator. Okay, it's not circulator. Let me talk about isolator because that's much more easier to explain. So just to refresh the concept of from concepts from the video lectures. So as you see, this is a schematic over here. So this is basically a circular waveguide. Okay, circular waveguide. And for the circular waveguide, both the ends, I mean this end and this end, if you notice, both of them are tapered towards rectangular sections. Okay, so circular waveguide with rectangular cross section ends. Okay, so it's tapered towards a rectangular cross section. And what is the purpose of an isolator? So the isolator will take care that in one direction you have a lossless transmission, okay, and in the opposite direction there is complete absorption and there is no transmission. So in one direction you have lossless transmission, and in the other direction, in the opposite direction, there should be or there must be complete absorption. Okay. Now, how does a ferrite material ensure this, or how does this Faraday rotation isolator works? So, which is the ferrite material here? So, this is the ferrite here. Okay. Now, so this ferrite rod, okay, so I can call it as ferrite rod. This will introduce a phase shift. Okay. So, any idea on what it will depend on? So this ferrite rod say has a length, I can say like length L. So what will be the phase shift introduced by that ferrite rod depend on? Any idea what those could, I mean, what is that phase shift dependent on? So for a length L, what will be the phase introduced? It's a very simple concept which we know from very basic transmission lines everywhere we have seen. So say you have beta times length. Okay. So beta is nothing but 2 pi by lambda times L. So if the ferrite rod has a length L, multiply that by 2 pi by lambda will give me the phase shift introduced by that. Okay, let me not write it as 2 pi by lambda because I wanted to generalize it. So let me write it as beta L. So what you see is L is the length of the rod and beta is the propagation constant. So propagation constant, as I mentioned in the previous question, what is propagation constant dependent on? It is dependent on omega, epsilon, mu and k in case of a ferrimagnetic or ferrite device. Okay, so the propagation constant is dependent on the material used. It's epsilon, mu and k, and the what is the length of this? that will also determine what is the phase shift introduced by the ferrite rod. Okay. Now, coming to in case of isolator, what will be the phase shift introduced? So that comes out to be 45 degree, which is what you have answered before. So the phase shift introduced by this particular rod in case of an isolator is 45 degree. Okay. Now how this whole thing works, you can see at port 1 you have an incident field or incident electric field. So this incident electric field, as you can see, it's passing through the rotating vane. So this is called as rotating vane 1. And then you have a ferrite rod. Then 2 is again a rotating vane 2. Okay. Now, when the incident field is coming to the rotating vane 1, this is perpendicular. So this electric field is perpendicular to the vane. So this will pass through. Okay, there will be full transmission. There is no absorption. Then once it passed through the ferrite rod, there will be a phase shift, which we know as 45 degree of phase shift. So once it is coming out of the ferrite rod, say if it is E incident, so that E incident will become E incident dash, okay, which is nothing but E incident angle 45 degree. Okay, so assuming that there is no loss or assuming that the amplitude remains constant. Okay, let me just focus on the phase shift. Now again, once it comes to the rotating vane 2, again it is again it is perpendicular. So again it will pass through. So there is a full transmission or a lossless transmission from port 1 to port 2. Okay, but there is a phase shift between port 1 and between port 2. What is the phase shift? That will be 45 degree. Okay. Now, so in isolator, the port 1 to 2 lossless transmission, whereas port 2 to 1 there should not be any transmission, there should be complete absorption. Now how does it happen? So to understand that, first you imagine, so here it's entering this port. Suppose there is a E incident from at port 2, it is passing through the rotating vane. Again there is no absorption or something, it's just fully passing. So again it is passing through the ferrite rod. What happens? It's again having a phase shift of 45 degree, and then it becomes parallel to what? This rotating vane 1. So once it's become parallel, what happens? This will get completely absorbed. So whatever be the incident field, that gets completely absorbed in the rotating vane 1. And any kind of reflections going back will be absorbed by rotating vane 2. Okay. So that is how this Faraday rotation isolator works. Okay. So I hope you will be able to answer the question on Faraday rotation isolator. Basically, so I have just mentioned some of the very basic concepts. I hope you from this you will be able to answer the assignment question. Okay, coming back to another question. Suppose a biased ferrite medium produces Faraday rotation of minus pi by 2 radian per meter at a frequency omega. For such a medium, the relation beta plus is equal to pi plus beta minus holds. Okay, so let me try to remind you about this particular equation, which I have told in the beginning. So phi, so the rotation angle is minus of beta plus minus beta minus by 2 into z. Okay. So based on that equation, if I write here phi is equal to minus beta plus minus beta minus divided by 2 into z. Assume that we are taking z is equal to 1 at some distance is z1. Okay. So in that case, I can just eliminate this number. Okay. So and the phi Faraday rotation, suppose this Faraday rotation angle is minus pi by 2. So minus of beta plus minus beta minus divided by 2. 2 and 2 cancels, negative and negative gets cancelled. So what we can write here is beta plus is equal to pi plus beta minus. Isn't it? So this holds true. I hope this is clear. Okay. Okay, now I have a few MCQs. I request everyone to answer them. The questions. Let me start with this particular question. Example of a non-reciprocal device. So you know what is a reciprocal device? Say you have same transmission from 1 to 2 and 2 to 1. That kind of a device is called as reciprocal device. So which is not a which is a non-reciprocal device among these? Yes, that's a circulator. So all of you know the working of a circulator. Suppose you have 1, 2 and 3 ports. So from 1 to 2 there is transmission, and if you give an input at 2, it will only be transmitted to 3. And if you give an input at 3, it will only be transmitted to 1. So that's a kind of transmission in case of a circulator. So it can be called as a non-reciprocal device. Now, next question. Ferrite isolators are dashboard devices. How many ports for a isolator? Yes, that's a simple question. It's a 2-port isolator. Okay, let's see this question. Matrix of an ideal isolator is not unitary, symmetric, lossless. None of the mentioned. So let's see what is an isolator again. Remember, isolator means in one direction you have full transmission and in the opposite direction you have full absorption or there is no transmission. So basically we can call it as this is lossy and this is lossless transmission. So that is a kind of an ideal isolator. So in case, so the question is, if you write the scattering matrix of that, what is the property it will have? So if you just imagine, I think there are some confusions. If you just imagine one thing, if it is a lossy transmission, if it's a lossy transmission, so in when we whenever we write as S matrix, if in one direction or any transmission, so S12 or S21 or whatever it may be, if it is lossy, then it's not unity, right? If it is 1, that means it is fully transmission. So here we don't have a full transmission, it is lossy transmission, it is not unity. So we can say that it is not unitary. Okay. That is something which we can say for sure. For other properties to hold, we have to make sure that we know each and every port's transmission parameters. Okay. Now, It's a application kind of question. Let's see how. Just let's give it a try. Okay. A very common application of isolator is to provide isolation between a low power source and the load. Is it true or false? So I would like to highlight this. Maybe you will just get an idea. Is it a low power source and a load? Generally, what is the purpose of an isolator? So it ensures that there is transmission only in one direction and there is no reflections going back and which will affect the source. Okay, so which is very crucial in case of a high power source. Okay, so this is a false statement. It should be high power source and a load. Okay. Okay, let me just move on to so let us see phase shifters in common. So as I told, ferrite devices introduces a phase shift. So let's talk about phase shifters also. Okay, a few questions on that. Uh, Phase shifters are used in what kind of antennas? Where the antenna beam can be steered in space by electronically controlled phase shifters. Yes, all of you are right. It is phased array antennas. Okay. So we all know, I think all of us know what is a phased array antenna. So if you have an antenna beam like this, if you want to steer it, okay, if you want to make it like this, like this, like this, like this, so you could steer the beam. So this we call it as beam steering. Okay, to do that beam steering, what is to be done? There should be a phase shift introduced. Okay, say if you have two uh, arms, what you need to do is one is E naught and one needs to be phase shifted. Okay, so appropriate phase shift should be given. So if that appropriate phase shift comes, based on that, the antenna beam, so the beam maximum will be steered. Okay, that is the very basic principle of beam steering in antennas. Okay, let's go on to the next question. Reciprocal phase shifters, okay, give different phase shift in different direction. It's a question about reciprocal phase shifters. Imagine what is reciprocal and what is phase shifter. So if you just combine these two ideas, you will be able to answer this question. Yes, Arundraj, you are right. Reciprocal phase shift should be giving the same phase in the different direction. Okay, so this is false. Okay, now we have a simple question. This is something which is related to the phase shift produced by the what you call the ferrite rod. Say you have a length L. This introduces some phase shift. So this is introducing a phase shift. So what is the question on? If a ferrite slab provides a phase shift of 48 degree per centimeter. So 1 centimeter length will give you what phase shift? 48 degree. Now, what is the length of the ferrite slab required to produce a phase shift of 180 degree? It's a simple question. You know that it's a linear relationship. So just give me the answer for the length of the ferrite slab to get the phase shift of 180 degree. Yes, right answer. Both of you have said the right answer. So how do we find it? 180 degree by 48 degree, that is giving you what? 3.75 centimeters. Again, next question has a little difference in terms of the units. So if you noticed, this is 0.836 radian per centimeter. So the question is, if a ferrite slab produces 1 centimeter gives me 0.836 radian. Okay, then how much is the length required to give a phase shift of 135 degree? Make sure that the units are in the same so that we don't have a answers, please. I am waiting. You can answer the question. You can try it out. Make sure that the radian is being converted to degree and then try to estimate it. So
2.81.
yeah, right. So once you convert this 0.836, you will get 47.89 degree. Okay. So this length should be 2.81 centimeter. I hope this is clear. It's a simple question. Okay. The next question is on the total number of ones in the scattering matrix of an ideal circulator is. So the question is about circulator. Just imagine what is an ideal circulator and imagine what will be the, when we say ideal circulator, the 1 to 2 transmission, then we have a 2 to 3 transmission, and then we have a 3 to 1 transmission. All these are full transmissions. So what will be the reflection coefficient, or what will be the scattering matrix? So I would like to ask you first this question. What will be the diagonal elements of this matrix? If it's an ideal circulator, what will be the diagonal elements of this scattering matrix? Yeah, that is true. S11, S22, S33. Okay, which is nothing but the reflection at port 1, reflection at port 2, and reflection at port 3. So those will be 1 or 0. So if the ports are matched, okay, if the ports are matched, perfectly matched ports, then yes, it is dependent on the number of ports. So what I am trying to say is, if it is a three-port device, I mean three-port circulator with 3 ports. So if it is perfectly matched, there won't be any reflections. So the diagonal elements will be 0. Now coming to what is the working of an isolator? There will be one transmission, that is from 1 to 2. But 1 to 3 is 0. Similarly, 2 to 3, there is transmission. Again, there is 1. Then 3 to 1, there is transmission. Again, there is a 1. Okay. So these are full transmission. So total number of ones will be 3. Okay. So take this as a 3-port circulator. Okay. Yes, your comment is very right. say suppose it is dependent on the number of ports. So taking it as a 3-port circulator in a general condition, this question has been framed. Okay, I hope this is clear. Now, a circulator device can also be used as an isolator with a few modifications. So, can we use a circulator as an isolator with some few modifications? Just remember one thing, in a circulator, it is possible that there is full transmission from 1 to 2 and there is no transmission from 2 to 1. So this is very important. So there is a possibility, right, to use it as an isolator. I request you to comment on what you think. All of you please respond what do you think. Can we make isolator with a circulator with some modification? Yes, I think all of you agree to that. So with some modification, a circulator can be used as an isolator. So then what is that modification? So in case of a circulator, you say you have, assuming that there are 3 ports and there is transmission only from 1 to 2, and there is no transmission from 2 to 1. And suppose if you terminate this port 3 with a non-impedance, okay, if you terminate this with a non-impedance, then you can use it as an isolator. So this is a true state. Please excuse me for a while. I'll be back in a couple of minutes. Hello. So there is a issue with weather in at my place, so I might lose power or I might get the internet disconnected. So let me just continue till it's okay. So in the scattering matrix representation of a non-ideal circulator, the diagonal elements of the matrix are. So this is about a non-ideal circulator. So here I spoke about an ideal circulator. Okay. So the ideal circulator, the diagonal elements will be 0 because all the ports are perfectly matched. How about a non-ideal circulator? So I think in the last question you told this is the reflection coefficient, right? S11, S22, S33. So these are reflection coefficient at the port 1, 2, 3. So the right option will be reflection coefficient gamma. So any doubts in today's session which you would like to ask? Yes.
Well, simple question. How to convert that radian to degree, madam? I don't
Okay.
know. That's
Okay.
what
So once if you want to convert,
0.8.
multiply this by 180 by pi. 0.836 multiply by 180 by pi will give you this answer. Okay.
Okay, madam. Answers again.
So I wanted to talk about in general about this anisotropic material. Say generally in electromagnetic theory, whenever we discuss about plane waves in a medium and all that, we look at say mu, the parameter mu, the relative permeability or the permeability. Let me talk it as tell this as permeability. So this permeability is being generally taken like in case of a homogeneous medium. Okay, in case of a homogeneous medium, you have a constant value for this permeability. That means in all the directions, it is the permeability is same. Okay, but so this is case of isotropic material. Okay, isotropic material. So you have this mu constant in all the directions. Say you take mu along x direction, mu along y direction, all will be the same mu. Okay, that is what I wanted to convey. But in case of anisotropic material, okay, so the simple example of anisotropic material is this ferrite device. Okay, so this ferrite device is a example of an isotropic device. So in such devices, you have an anisotropic permeability. Okay. Generally, for example, I would just try to write it. Suppose you have a magnetic field. Okay, you have a magnetic field along x direction. Okay, so I can write the matrix mu as mu naught mu mu 0 0 0 0 jk minus jk. Okay, so the magnetic materials are generally defined in terms of mu and k, both the values. So you can notice the anisotropic material has permeability, different permeability values in different direction, and it also depends on the direction of the magnetic field. Okay, suppose you have a magnetic field along z direction. Assume, okay, you have magnetic field along z direction. So what will be the matrix here? I am writing the same permeability matrix. So that will be mu naught, okay, jk 0 minus jk 0 0 0. Okay. So the anisotropic material will definitely have different permeability in different directions. So that is what I wanted to convey with this idea of the matrix. So I hope you will be able to answer most of the assignment questions from these discussions. So if you have any doubts, you can ask me. As I said, weather is little bad here, so I might lose the connection. You can, meanwhile, you can try to ask if you have any doubts.